and today we will be discussing the basics of machine learning and doing a simple linear regression example. So machine learning is all the rage, but how does it differ from traditional computing? So in traditional computing, you have data and you have some type of program or algorithm which you would like to apply to that data to get a particular output. This is good because a computer allows you to very quickly and efficiently apply that algorithm to the data and transform it. But a limitation of traditional computing is that program or relationship has to be known. What if you don't know the mathematical relationship between an input, your data, and the desired output? That's where machine learning can come in and assist. In machine learning, you have labeled data, and what I mean by labeled data is data that has its input parameters and its respective output that we want to observe and predict. We want to determine the mathematical relationship between this input and this output. And we use machine learning and the computer to do that, to determine this mathematical relationship. And what's powerful is then we can apply that relationship to new data sets to make predictions. Machine learning is particularly helpful if the data set that we are inputting and wanting to use to train the mathematical model is abstract or complex, such that our human brains would not be able to efficiently draw conclusions and relationships within the data. There are types of machine learning, such as supervised and unsupervised. Today, we will be discussing a supervised machine learning model. In supervised machine learning, you will train the computer with the labeled data. Example that I will be doing in this video is looking at the heights of parents to predict the height of a child. So what labeled data would look like is we would have our index, our input parameters, in this case parent A and parent B, and then the label is the height of the child. That's what we're wanting to predict. So in order to train the computer, we have to show it what an output is for particular inputs. So what we're going to do is we're going to take that data. Now, usually when it comes to you, it's in a table of some sort, and we can use tools in Python like pandas to create visuals, perform calculations, and then via machine learning make predictions for what the outcomes would be for new sets of data. If I continue with the example of the child's height, I'm going to create a fictitious data set that will be 100 records long, and I'm going to put it in a pandas data frame. What you would do next in real life would be to clean the data, but ours is squeaky clean because we made it. So it wouldn't have any nulls, and it would be correctly formatted and ready to send through our machine learning pipeline. The first thing you should do once you have your data is to explore it by doing some simple calculations, such as to determine correlations within the data and using visuals to explore the distribution, using histograms or scatter plots, or even looking at the relative amounts in categorical data using pie charts. After you have explored the data and understand superficially any apparent relationships between your features and your label, or your input parameters and your desired label, you need to split the data into the training and test sets. This is actually the first real step that is considered machine learning. And what these sets do is they function as the training set to help the computer learn what the relationship is between the input and the output, and then the test set will evaluate that model. To make sure your model isn't biased by the test data, it must be removed before any model building occurs. You may ask yourself how big these two sets should be. The training data set should be large enough to adequately teach the computer to fit the data, but the test data should be big enough to probe the strength of the model adequately. So really, you would ideally have both of these sets as big as possible. However, that would be counterproductive, because the bigger one is you begin to sacrifice the other. So there should be a random split in the data. What I mean by that is there shouldn't be any filtration based on a particular feature, as that would bias the model building process. And your training set should be larger than your test set, because you want to adequately train the model. That's what's very important. The test set is just there to evaluate. But again, you want it to be a comprehensive evaluation, so you wouldn't just stop at one example. What a textbook example of a split would be a 70-30 split in the data. So for our example today, which is 100 records long, that would mean that 70 would comprise our training set, and then 30 would comprise the test set. Model selection is what comes next. And as I told you at the beginning of this video, we will be doing a linear regression example today. And really the best way to determine what type of model you should use is to ask yourself, what does the label look like, and what question am I answering by applying machine learning? In today's example, we are making a quantitative prediction, which is how tall is a child. That's going to be a number. Therefore, a regression model is best because it will produce a quantitative output. We are going to be starting with linear. There are other higher order relationships, such as polynomial regression, that could be applied, but let's start out simple, and linear is more intuitively able to be understood than higher order. It's also easier for me to draw for examples. So as I said, linear regression is where we're starting. So a single linear regression would be a mathematical relationship between a single x input and a y output. And all we would be doing would be fitting a line to that data. Now, in our example today, which is very simple, we have actually two inputs, the height of parent A and the height of parent B. So, and forgive my limitation in drawing on a 2D surface, we would be doing a multilinear regression in that we're going to be fitting the contribution of two distinct independent x values. In other words, the height of parent A does not affect the height of parent B and vice versa. And what would actually occur here is we would be producing a plane that corresponds to the y data. However, it's difficult for me to draw that in 2 dimensions. So after we build our model using the training set, we are going to have to evaluate it with the test set. For linear regression, we would use R-squared. Essentially what R-squared does is it allows us to look at the ratio of deviation from our model and the data points. So what I mean by that is it calculates the residuals, and it determines how well our model counts for the variation in that data. So the closer to 1, the better the fit of the model. And we can apply that model then to new data to make predictions once we evaluate it. So let's move on to the code. The first thing I did was import my libraries, and I'll show this in an easier to read way later. I will be using sklearn for this example today. The next thing I do is I am going to be using a random number generator to generate my data sets. And in short, the parent A and parent B data sets are independently generated. However, the child data set has to be dependent on those two. And so I just determined the child data set to be the average of the two parents with some random variation in it. The first thing I do, I'm going to run this. The first thing that I do is I look at the correlation between the two input parameters. And if there are more input parameters, of course, you would look at the correlation between multiple. As I told you previously, the parent A and parent B heights are independent, and that's reflected by this figure here, which shows that there's no trend. The height of parent A and parent B are not correlated in any way, and that's also evidenced by the correlation coefficient when it was calculated. We then can move on to the relationship between parent A and the child. And we can see that at almost 0.6, and there does appear to be a correlation between the height of the child and the parent A, and that's reflected by a visual representation that as you increase the height of the parent, the child's height also increases. The same holds true for parent B, and the correlation coefficient was determined to be 0.63. Now, what about the relationship between parent A, parent B, and the child? So this is where that plane comes in that I was discussing. So it's easier to see in 3 dimensions here how the child's height is dependent on both parent A and parent B, whereas those two parent heights are completely independent of one another. Now that we've established our inputs, we can now apply a machine learning model. And like I said, I'm doing simple linear regression. So the first thing I do is I have my training sets and test sets made using the train test split from sklearn. I'm doing that 70-30 split that I discussed earlier, and I will be applying a linear regression model. I fit that linear regression model using the training data, and then I use that linear regression model to make predictions on the X-test data. I then have to compare the linear regression predicted data with the actual, so the Y-test, with the actual data. And I have a visual representation of that. We see that it's actually pretty good, and the R-squared was 0.88. Like I said, the closer the R-squared is to 1, the better the fit. And that's what the sklearn's linear regression score function does. It actually reports the R-squared between the test so our model and the actual output values. So this was a very simple example, and as I said before, I would be showing you an easier two-way read version of that code. So the first thing I did was import packages. I created the data. This was a super simple example. And then I made various plots. So these were all my scatter plots. And then I did a 3D plot of the parent A, parent B, and child height. Then I applied a multilinear regression model, first doing the split. So the first thing I do is split the data. I apply my model, I fit my model, I then compare it with the evaluation data, and I saw that it was actually pretty good. The next thing I would do in real life is apply my model to completely new data and use it to make predictions. So thank you all for tuning in today, and please like and subscribe and leave a comment for more videos that you would like to see. Have a great day.